Our next speaker is Professor B. Prasanna Venkatesh from IIT Gandhinagar. And the title of the slide is, of his talk is Light-induced density wave in a dipolar Bose-Einstein condensate.
Okay. All right. Fair. Okay. Good morning. Good afternoon. Close to afternoon now. As Joey introduced, my name is Prasanna. It's a pleasure to be here. I thank the organizers, all three of them. And in fact, this is my first AMO conference in India. I've never been. So I just wanted to introduce myself. I'm Prasanna. I'm at IIT Gandhinagar, and I'm a theorist working. I have like 3 interests: quantum optics, ultracold atoms, and also quantum thermodynamics. So as this slide shows, let me begin by saying what I'm going to be talking about, because I don't know if I'm going to get through what I want to talk about, but if at all you have to leave with a message, let me just give you a 1-slide summary of what I'm interested in this talk. So I'm interested in considering a dipolar Bose-Einstein condensate, dipolar meaning these are magnetic dipoles, and I'm subjecting them to 2 counter-propagating but orthogonally polarized light, which is a nice accident to the previous talk. I didn't know how the random thing came up that these are also the exact same lin perp lin kind of configuration, except I'm interested in completely far detuned light. So there is no scattering between the 2 beams. And since they are orthogonally polarized, they're not forming a standing wave. So this is definitely not an optical lattice. But what happens is that there is going to be long-range interactions introduced by 2 features in this system. One is the magnetic dipole-dipole interaction. And then there is going to be the light itself, which will introduce another kind of long-range interactions. I'm interested in the interplay between these 2 interactions. More specifically, such long-range interactions lead to a very fascinating feature in the excitation spectrum of this Bose-Einstein condensate, basically how the Bose-Einstein condensate behaves when you kick it. And this feature is called a roton, or a roton minimum. And then this also leads to a very fascinating state of matter called supersolid, where you have basically a periodic density wave, hence the title density wave, coexisting with superfluidity, which is there in Bose-Einstein condensate. And now the point is you'll have 2 independent sort of long-range interactions causing this kind of a feature. And I'm interested in the interplay between them. It turns out that it's not an additive effect, and that's why it is interesting. Okay, so that's the main message of the talk. So let me then move on a bit. All right. So of course, now I'm in a privileged position where I have to almost do no work. I have people working with me, like Chinmay, who's in the audience, who's done all of the heavy lifting for this work. She's my postdoc. She's an early career fellow postdoc at IIT Gandhinagar. I really encourage you to go to a poster, talk to her. She's done all of this work. And this is in collaboration with a couple of other friends. One is Stefan Ostermann, who's in Harvard, who used to be in Innsbruck, and Farok, who's also a postdoc in Innsbruck. And moving on. Okay, and here's a very brief outline. I'm just going to introduce this whole features, this whole field in some sense in a very, very broad way, and motivate why I'm interested in what I'm interested in. Then I'll basically give the theoretical description of a dipolar BEC Bose-Einstein condensate subject to these laser EM fields, and then I'll describe some results. Okay. All right. So since I talked about Rotons and supersolidity and so on, let's go to the mothership or the mother load of this stuff, which is superfluid helium. Helium-4 is one of these very rare objects, natural objects, which when you go to even extremely low temperatures, it doesn't solidify. Instead, it goes into this exotic state, which is a superfluid. And when you look at basically the excitation, elementary excitation spectrum of helium-4, what happens is basically, what do I mean by elementary excitation spectrum? The ground state of helium, let's say it's some uniform state, and I'm interested in what is the energy when I try to kick the system with different wave number densities. So I'm imprinting some density waves, and I'm asking what is the energy of these density waves. And now a particular aspect of this, what I'm interested in is the shape of this energy spectrum. And this energy spectrum was theoretically calculated, or at least phenomenologically calculated by Landau and Feynman. I'm not going to go into the details of it, but what is important for me are a couple of features. The first feature is if I'm at very low momentum number, very long wavelength fluctuations, the energy goes linearly. So this is a sign of phonon. So basically, if you kick, you get phonons out. But that's not all. If I go to slightly larger K, I actually get a minimum in the energy spectrum. Okay, and this minimum is called a Roton minimum. Okay, and this is interesting for a couple of reasons. First of all, if you have this superfluid, this Roton minimum sets the critical velocity of the superfluid. But even more interesting is the fact that this points to something very beautiful that can happen if, by some way, I don't know how to do this in superfluid helium easily, but if you imagine, I can keep pushing this minimum down and more down towards the x-axis. Let's say it touches the x-axis. When that happens, one says that this Roton minimum has softened. When that happens, what you have is something fascinating. What you have is that you have a zero energy excitation of the system, but at a finite wave number, which means the system is susceptible to density waves at 1 over k. Okay? And now, if you have a density wave with some finite periodicity in a superfluid, you have a supersolid. Okay? So that's the fascinating aspect. But it turns out that helium is a notoriously difficult system to work with, theoretically, especially, because it's extremely strongly interacting, and the connection, exact connection between the Roton minimum and whether you can have a supersolid in helium is not completely understood yet. Which meant we do what we do in ultracold atoms, we can quantum simulate it, in the sense that I can look and ask, is it possible to get Rotons with Bose-Einstein condensates? If you look at it in a very naive manner, if you take your garden variety Bose-Einstein condensate, let's say with alkali atoms, rubidium, and so on, what happens is basically this is a very weakly interacting superfluid. So the interactions are not nearly strong enough to give you basically the features that were existent in the superfluid helium. Another way of understanding why this is happening is that apart from the weak interactions, the nature of the interactions is also important. So the nature of interactions that you use to describe Bose-Einstein condensate is this kind of contact interactions. If two atoms are on top of each other, they have some interaction, but otherwise they don't interact. Then this means that this is a delta function in position space. If you Fourier transform it, then you have all k modes. So there is no preferred k mode, so you would never expect some kind of Roton minimum in this. But all is not lost. You can consider slightly different kind of Bose-Einstein condensates, and that's where these dipolar Bose-Einstein condensates come. So what you can do is you can consider a Bose-Einstein condensate with magnetic dipole moments, or you can also induce some dipole moments using electric fields, whichever means you do. All that you need to do is you need to introduce this kind of a extra interaction term that goes in this form. For this configuration, which is the only configuration I'll be thinking of in this talk, I have a cylindrical Bose-Einstein condensate with my dipoles pointing along x, and this is my axial direction. In this kind of a configuration, my dipole interaction has this form. The most interesting aspect of this dipole interaction in position space is it can be attractive or repulsive, depending on where you are, where two dipoles are. And that's going to play a role in getting a Roton momentum. But if you Fourier transform it, in momentum space, it will also have some interesting behavior. But the momentum space picture is somewhat hard. So I'm going to give you a small sort of idea of why you should expect a Roton in this kind of a scenario. The idea is really cute and simple. What happens is basically, so if you want to believe me and say that there has to be some kind of a Roton minimum, you have to convince yourself that you should be able to lower your total energy of your Bose-Einstein condensate by forming density waves of particular wave number. Then I'll know that I can suspect there can be a Roton minimum. Let's show that happens. So for example, if I have low momentum, if I look at low momentum excitations of this gas, then my dipoles are going to always be side by side. So this means that x is going to be 0, right? Which means this term is always positive. So my interaction basically just adds to my contact interaction, and it just doesn't do anything to the spectrum. So adding the dipole interaction doesn't do anything interesting. On the other hand, if I look at a slightly larger momentum mode, if I have along the Z direction, if I look at a momentum mode that has a slightly larger wave number and smaller wavelength, then I have a chance of piling up these dipoles on top of each other. So head to tail. This interaction is actually attractive because in that case, your X and R are exactly the same, and this would just give me a negative number, which means this attractive interaction can lower the energy of my system. But if I just go crazy and keep making my K very large, eventually my kinetic energy because of the density waves and the contact interactions itself will win, and my energy will increase, which means there is a in between carefully chosen K at which I should have a minima. And that K, very simply by looking at what should drive that K, it's very simple to see. If I have basically a wave that is of the same order of magnitude as the extent in the X direction itself, which is set by the trap that makes my cylindrical BEC, that extent, if my K is 1 over that extent, precisely at that in-between point, I'll be able to accommodate enough dipoles to have this attractive interaction win and get a Roton minimum. So this is the physics of how you would get the Roton minimum in position space. But there is a catch. The catch is that this attractive interaction has to win over this contact interaction that is repulsive. And that will happen only when you have really large magnetic dipoles. And for a long time, this was an issue in the community. So the first set of dipoles, dipolar BECs that were made were with chromium, and they were not too large. And what would happen is this would modify the spectrum a bit, but you will never get an appreciable minimum, let alone softening it. Okay, so that's the idea. Now, since this was the status, people started looking at slightly other systems where you could get Rotons. But now, this is a slightly different direction to get a Roton. In this case, what you do is you have an Bose-Einstein condensate and confine it in a cavity. Okay, when you confine such a Bose-Einstein condensate in a cavity and you apply in the transverse direction, you apply a standing wave laser light. Now, what's going to happen is this standing wave laser light is going to induce interactions, and these interactions are going to be infinite ranged. To see why it will be infinite range, just imagine what is causing the interaction is the fact that this entire Bose-Einstein condensate is interacting with essentially a single standing wave mode of the cavity. And it sees so the standing wave sees every atom. So there is no sort of real position dependence to the range of interaction. So that every atom in this cavity will talk to everyone else with the same strength. And this means that the interaction is infinite range in position space, which means it has to be very sharply peaked in momentum space. And that you can understand physically, because how does this interaction work? It comes from a fundamental process, which is just Rayleigh scattering. So what happens is you can basically break this standing wave into 2 traveling waves. There are 4 processes that can happen. Because this is extremely far detuned light, I will only have Rayleigh scattering. I can basically absorb a photon in this direction, emit in this direction or this direction, or absorb in this direction and emit in this direction or this direction, because this is the cavity direction. So the equal superposition sum of all these modes is basically the single density wave mode that I can excite. Okay. Now, what happens is that when you look at the energy spectrum for this mode, it has again, so it's actually a little bit easier to see why you should have a super solid in this case, rather than how the Roton minimum comes. In fact, that was the direction in which the experiments proceeded. The first experiment showed that you can get a super solid here. Let me very quickly explain that. What happens is you have this kind of a setup. I have an optical lattice in this direction. And if I have basically a uniform Bose-Einstein condensate, this is like a completely inhomogeneous scatterer. I will not be able to scatter light into this cavity when I have very low power. Basically, phases will cancel from different atoms in the Bose-Einstein condensate. There'll be no buildup of light. But if I increase my power above a certain critical power, then this particular density wave I talked about, corresponding to these scattering processes into the cavity, these density fluctuations start getting seeded, and then there will be a runaway process, because as soon as you start scattering light into the cavity, you will develop an intra-cavity standing wave potential. And this runaway process is enabled basically by a Roton mode, which is basically the energy of this particular excitation going to 0 as you tune the power. So this is a slightly different way of looking at the Roton spectrum, because remember I showed you a spectrum where I showed E versus K. Here I have just fixed my K. My K, the mode that I'm exciting and which is going to 0 is just one mode, and that is completely fixed by the cavity, which is somewhat of a disadvantage, because you wanted in the superfluid helium or in the dipolar condensate, you could sort of tune this K by choosing your trap along the axial direction. So that was one disadvantage with these schemes. And it turned out that you can sort of overcome that a little bit. Oh, this was not meant to happen. Maybe I pressed it. That's very strange. Sorry. Okay, yeah. So there is another scheme with, again, inducing interactions via laser light. This is precisely the configuration I talked about in the first slide of my talk, where I have counterpropagating laser light, still no dipolar BEC, just regular rubidium type BEC. And in this case, you again have, when you have basically these counterpropagating laser beams, there is no optical lattice potential to begin with. Hence, the gas is going to be homogeneous and in this cylindrical configuration. But eventually, if you increase your power at some critical power, basically you will have a density wave developing, and at the same time, you will actually have backscattering of light by the atoms, and a lattice will also be set up by the atoms themselves. So don't worry about this. This is the subject of the talk, and I'll go into the theoretical description of this in more detail. But safe to say that the Roton momentum you get, this is more of a picture that looks like the original Roton picture. The Roton spectrum, that the point where you get the Roton minimum, in this case, still the momentum mode has some dependence on the system parameters. For example, it is set by the density, the average density of atoms you have. Okay, so that's, and the last thing I want to say in this introduction, I don't know what's wrong. There is some lag. Yeah, I think it just. Yeah. Oh, I just have to wait for a bit for the lag. Okay, now it's fine. I think no, we are going very back. No. Let me just go to.
Yeah, you can just click on forward.
Yeah.
Just go slowly.
Okay, sorry about that. Okay, so we took these different routes to make Rotons by using light-induced interactions. But meanwhile, over the last 10 years, there's been amazing development with purely magnetic dipolar Bose-Einstein condensate. So we have newer and newer species of atoms. With that, you could actually have atoms like dysprosium and erbium, where the dipole moment strength became really large. And there have been experiments, for example, where they have measured, this is just literally the spectrum of a cylindrical gas of dysprosium atoms, and you can actually map out the Roton spectrum using Bragg spectroscopy with these atoms. And at the same time, you could also see the different phases where if you make this Roton minimum smaller and smaller, you can do that by making the contact interaction or the collisional interaction smaller and smaller. You can eventually soften this, and you can get super solid phases, where these are basically phase contrast images, which is like density in position space of a Bose-Einstein condensate that becomes a super solid, a dipolar Bose-Einstein condensate. And in fact, you can also kill this super solidity in a sense by basically making sure that if you keep making this density wave stronger and stronger, eventually the different density peaks inside this super solid will not talk to each other, and you lose phase coherence, and you get a newer phase of matters called droplets, or an array of droplets. And you have phase coherence. This is basically the momentum space picture. So you have phase coherence for a super solid, but with these droplets, you have no phase coherence. Okay, so good. So now that there are these two independent ways of introducing Roton spectrum with ultracold gases, my interest is essentially in this talk to combine these two things and see the interplay between them. So to do that, let me actually quickly go through the theoretical framework. The theoretical framework is basically a Gross-Pitaevskii equation. In this case, I have and the system is basically, as I said, a cylindrical Bose-Einstein condensate with dipoles pointing along the x direction. This is my Gross-Pitaevskii equation. This is my kinetic energy. This is some external potential, which is the traps, and also it will include the light in a moment. This is the contact interaction. This is the magnetic dipole interactions. And this is a term that I'll come to in the end. This is a term that is a quantum correction. This is not necessary to introduce a Roton minima or soften it. It is needed, in fact, to stabilize this supersolid phase that eventually emerges. Okay. So I'm not going to go through the exact expressions of this. We can go through this later. But there is a problem with this theoretical description in the sense that it is extremely hard to do a full 3D Gross-Pitaevskii calculation. It's computationally intensive. And since we have sort of developed our intuition, if you remember, based on this 1D sort of model for why there should be a Roton, it might be useful to actually develop an effective 1D description, but keeping the fact that in the transverse direction, I have some dynamics. So this is done by a variational effective version of this Gross-Pitaevskii equation, where I still keep my wave function or my order parameter along Z. I'm interested in this object. I'm going to solve for the dynamics of this object. But in the orthogonal direction, I basically have a Gaussian, but the anisotropy between the Gaussians and the width of the Gaussians become variational parameters. So I minimize it at every step. Okay. So that's the structure. And that, of course, changes how your contact interactions and other objects look. But this is not so important. But this can be done. And this is the framework that we are interested in. And now, since this is just a description of a dipolar BEC, now let's look at how light enters into this whole picture. So this is very important. What I now have is an external potential that is given by this box potential, which is going to contain the atoms, essentially making sure that the external potential along Z is homogeneous to make the physics simple, and extra potential that is going to come from the applied light field. From the point of view of the light field, I'm going to treat the atoms as simply linearly polarizable particles. So I have two laser beams from left and right of exactly orthogonal polarizations. And then the optical potential they will produce is precisely just the magnitude squared sum of the two times the polarizability alpha. Okay. This is just simple, and this alpha will depend upon the detuning and so on, but it's just a simple, if this were just one standing wave field, that would be the optical lattice. But now this is not. These are two plane waves. Okay. And in principle, when you begin with a very small laser power, this is exactly a uniform potential to begin with. Okay. Fine. So that is the description of what the light does to the atoms. But the interesting thing in the system is that the atoms are also going to backact on the light, which means you have to solve for how your electric fields evolve as a function of position and time. But we are going to simplify the time aspect of this. You would write down the Maxwell equations for these electric fields, and you would have the Helmholtz equation. There would be a time derivative of E on the right, but I'm going to set that to 0, which means I'm going to assume that my electric field adiabatically adapts to whatever density profile of the atoms I have. So there are no propagation, there is no retardation, all these effects are gone. So this is a very simple time scale separation effect, which you can do. Okay. Good. Once you do that, then there is this single parameter that appears in this Helmholtz equation, which will quantify for us the strength of the interaction between light and atoms. So now what I have to do is I have to solve, let me go to the next slide. Sorry, yeah.
But if both the lights are detuned too much, then do you expect this coupling will be strong? Because coupling will be then away from this, isn't it? The resonance. So,
fine, but I can enhance it as much as I want. I have also the scaling with the number. Yes, yeah. Okay, so.
You did not consider the temperature of the atoms
T0.
in your GPU, T0.
T0.
So, but practically speaking, it will be something on the order of 100 nanokelvin or so for a condensate.
Sure.
So how your like predicted like let's say the models and etc. will differ from the actual observations with this?
So this is at the same level as how well you can model. Let's take a usual Bose-Einstein condensate and you excite some modes and you study the mode spectrum with. You would use a Gross-Pitaevskii simulation. Whatever error there is there in such simulations in agreement with the experiment, it will be the same.
My point is, yeah, I understand all these things, but my point is, how difficult is it if you consider the temperature in the Hamiltonian?
It's a little bit difficult because what you have to do is, if you want to consider temperature, the simplest way is to have some kind of a two fluid model, right? Or not fluid, but two component model, where you would say there's a thermal cloud. And then you have to consider interactions between the thermal cloud and the BEC. And then you have to write down an extended version of GP that includes both. This is possible, but this is such a messy thing that unless it gives you some new physics, you wouldn't do it. As far as I know, it doesn't lead to any very interesting physics, except in some really, if you do some very big quenches or something, you have to be worried about that. Okay, I see I'm running out of time very quickly, but this is the final sort of coupling equation, where I have a Gross-Pitaevskii equation that couples basically, that gives me how my BEC wave function evolves as a function of time. And I have an equation and my light field occurs as basically a potential, external potential in the Gross-Pitaevskii equation. And my light field has an evolution equation by itself. And these are coupled equations, and I have to solve both of these equations simultaneously. And the boundary conditions for my light field equations is that I start with some laser from left and right of a given intensity IL and IR, but I'll use the parameter C, which is the amplitude of the laser light. That will be my control parameter. I'm interested in the behavior of my system as a function of this control parameter C and the dipole strength. Okay, that's my. So, okay, so a quick sort of thing on thermodynamic limit here, because this is a little bit important because I'm going to float around things like phase diagrams. One has to be a bit careful. The standard thermodynamic limit with just dipolar gases without light is you take N and L to infinity and you keep a finite density. Now, if you do that, what happens is these light-induced interactions, because they are infinite range, they will blow up. So that doesn't make sense. On the other hand, in this earlier version of this paper by Stefan, who's also working with us, they had a slightly non-standard thermodynamic limit for these infinite range interaction systems, where you keep N finite, but you make L infinite. Because it is an infinite range interaction, even if it is dilute, the light-induced interaction will actually always be present. But all the other competing interactions, like dipole-dipole interactions, will scale very poorly. So you will have no interesting competition between dipole-dipole and light-induced interaction. And so we are going to stick to finite N and L and see what physics comes out. That's our aim. Okay, good. So now we can go to some results. All right. So the first thing you would do, because I talked about Rotons, is actually do a following linearized fluctuation analysis. So I start with a uniform solution for the wave function. And basically my electric field is also just a simple plane wave, except my effective wave number now has a dependence on the mean atomic density. So it's just like some refracting slab. That's it at the beginning. And now I'm going to perturb about that and solve basically the coupled Gross-Pitaevskii and light equations and extract an excitation spectrum for different values of K. Okay, so that is my aim. When we do this delta psi is basically e to the ikzz. And when you do that, you get the linearized spectrum. Now, I want to analyze this spectrum. And I'm just going to show you very quickly that this spectrum will host three kinds of Rotons or three kinds of regimes. So now the spectrum is controlled by C, and it's also controlled by the dipole moment of the magnetic dipole moment strength. Or you can also think that it is controlled by the ratio of the magnetic dipole moment strength to the contact interaction strength, whichever way. I'm going to use D as a measure. But in real systems, D is fixed. It's the ratio of D to the contact that can be tuned. Okay, so now the first sort of spectrum is something that was already predicted with the magnetic dipole-dipole interaction. If I'm at a very small value of C and I increase my dipole moment strength, eventually I first get a softening and I get a Roton minimum, and eventually this Roton minima, this E squared becomes negative and I get a Roton instability for some K. And this is a magnetic Roton instability. And this happens, this K, the momentum K at which this Roton minima picks up is basically given by this 1 over the length scale of the transverse trap, and it's set by the transverse trap frequency. Then, on the other hand, if you basically keep the value of the dipole-dipole interaction very small and you tune this C, you get the other Roton that we talked about, where you actually end up with a Roton minima at this 2K effective. So this K effective is the effective wavelength of your applied laser, and you get a light Roton instability. Now, if you actually increase both of them together, what happens is basically you have a simultaneous Roton minima at both the 2K effective and the magnetic part, and they can both become unstable at some regime. Okay, and in general, we find that this light Roton for the system that I'm considering is much larger than the K Roton. And the interesting thing is now I can look at the phase diagram made up of such the excitation spectrum, where this phase is the phase where my so this is a phase where my Roton is stable. Okay, sorry, my spectrum is stable. And these are phases where my light Roton is unstable, a magnetic Roton is unstable. Here, both the light and magnetic Rotons are unstable. But the key takeaway, and in some sense from the whole talk, is that these boundaries are rather non-linear. They are not sort of just, it's not just a square boundary, which means basically these Rotons talk to each other. Let's see, for example, what is the light Roton, what is the light doing to the magnetic Roton? Basically, or the other way around, if you see the value of C you need to actually get a light Roton, by increasing the dipole moment strength, the magnetic dipole moment strength, you actually lower the threshold for this C. So that's the first effect. The second effect is if you look at the K that the D that you need in order to actually get a magnetic Roton, that is lowered at a higher value of C. And that is an effect that happens because your light Roton kind of pulls up your magnetic Roton unstable region and kind of stabilizes, in some sense, the magnetic Roton. So there is a rich interplay between this. And let me finish the last thing I want to show, because I think I'm out of time, right? Yeah, so sure. So yeah, so let me just show what are the density patterns you can get. So these are the usual density patterns. So this is a light supersolid. This is your array of droplets with magnets. On the other hand, when this light Roton develops, at the same time, when you look at the light field, it actually sets up an optical lattice. Until this light supersolid develops, you do not have an optical lattice inside. It is basically a simultaneous generation of this light supersolid and an optical lattice due to the scattering. And finally, this is the interesting region. Okay, so in this region, where both the light and magnetic Rotons are unstable, when you solve and find the ground states, you see a rich variety of ground states. There are two particular kind of ground states I want to point out. The first is in a regime where I have just crossed from the magnetic Roton instability and I have started inducing a light Roton instability. In this case, I actually get an envelope that looks like a bunch of magnetic droplets, but inside the envelope, I have basically a modulation that is set by the light Roton. So in some sense, there is still supersolidity within each droplet, but the droplets between them, it's not obvious if they are coherent or not, if they are phase coherent or not. On the other hand, I can also, if I keep increasing this light periodicity larger and larger, I end up with a much more sort of complicated density patterns where typically in principle, there is the magnetic Roton is there, but it's not giving you a simple envelope and they are not even perfectly periodic. They're sort of incommensurate and aperiodic crystals that are formed. Okay, so for the lack of time, I'll stop here and I'll just flash my summary slide and I'm happy to take questions. So the last thing I want to say is I can prepare these states with standard dysprosium numbers. This is something we've checked out. I'll just run this video as it happens. So this is basically a density, one of these light magnetic Roton forming. And at the simultaneous level, you actually start with no light, sort of no lattice, but then the lattice develops later due to the simultaneous interaction. Yeah, thanks.
In this case, we'll see the
multiple droplets. Multiple. I have a trap.
Is it possible to control the single droplet by tuning the light?
So you mean each droplet in the droplet array?
Yeah.
Yes, I mean in a sense that is what this space is, right? So this space I had here. So let me show you. Sorry. So for example, this phase, we have essentially done that. What we have done is we had initially, you can sort of prepare this phase by starting with an array of droplets here, and you can basically change the C. And when you change the C, you start actually developing these density waves within each droplet. That's what's happening. So that's why this, I'm calling this a droplet of supersolid. So the point is, since you're starting with droplets, okay, initially there is no supersolid in the sense of there is no phase coherence between the droplets. Now, all that's happening is there is an intra-droplet coherence that is developing as far as this density patterns go. Because I can sort of, for a single droplet, I can look at a mean field measure of superfluid fraction, the Leggett measure, and that will be finite. But between interdroplet, whether there is coherence, this is a question I'm not yet sure about, because this is an interesting question, because if you did not have the dipole interaction at all, and you looked at a completely laser light induced transition, I would say even if my density pattern had like nodes and it actually did not have like, it sort of went, there is no overlap between different droplets, the light solid, because of the laser, there is an overall phase coherence. So you would expect in this case for all C, let's say at D equal to 0, I would say I get a supersolid. But that is coming from a thought process of laser. But you have to do it with many, you have to actually do a many body theory to understand this. Otherwise, it's not obvious to see. Yeah.
Okay, one question here.
So hi, this is an extension of Shubhadeep's question, slightly different. So I assume that you are not considering that the temperature increase of the dipolar BEC due to the light scattering by your
so that's a very good question. So let me just show you one slide and will answer your question. So that is the limiting factor, right? What is really nice and that is really cool, I just found that out yesterday night. At least I found it out clearly yesterday night. Sorry for sort of moving slides around. I hate that. Okay, great. So the point is, with all of these things, the issue is that I'm actually shining lasers. I will heat the system. So now I have to look at what is the heating rate. So I'm plugging in the intensity that I require to see these ordered phases, and then I can calculate the heating rate due to spontaneous emission. It turns out that this heating rate is really small. What is really interesting is when the first proposal came out from Stefan and people without the dipole interactions, they actually required a much larger intensity. And that's one of the reasons why it has not been observed so far. It turns out because of this boundary going down, the C you need with the magnetic dipole interactions is actually lesser. So you might be able to quickly see this light induced order due to the help of these magnetic dipoles. That's one of the reasons why this is interesting. Yeah.
Question at the back. Oh, sorry, Shoikoda, you had a question.
So I have a couple of questions which might be related. The first one is that when you have the instability region, if I just look at the region without the instability, like that region, it seems like there are two kind of length scales coming up now, right?
Oh yeah.
Because you have a transverse direction, but now there's another magical. So what would be that? Is it power induced?
No. So you mean for the Roton instability?
Yeah.
So this Roton instability in the magnetic case actually gives you a band of K, which all give E squared negative. So a bunch of K modes, a continuous set of bunch of K modes actually become unstable.
And what sets that?
So that the center of that, the point where it starts going in, that is when the light is 0, it is set exactly by the transverse trap length, because that made sure that this top on top argument I made. But that has a very interesting consequence that distinguishes this light and this crystal. It's compressibility. The point is, if I have more modes, the supersolid I produce with these magnetic interactions, this is more clear with I can show you later the preparation thing. The solid I make with the magnetic supersolid, that can actually oscillate and it's softer. On the other hand, the light solid, if you looked at the Roton, it's like a single bang-on momentum at which I soften. So it's like pinned. In fact, as soon as I get a light solid, it doesn't move anywhere. So you can really distinguish between the two, and this in-between guy has a bit of both.
And the second question is related exactly to this, so is there the reason you're saying that between the droplets you don't expect phase coherence, is that because of some many body interactions? Because otherwise your system seems to be, there's no.
So let me say this, and then if I'm wrong, Regis should correct me. So what I think is the following. So if I'm doing a GP equation, it's nonsense to even say whether there is phase coherence, because I have a phase coherent order parameter. So there is always phase coherence if I'm in GP. But think of it like this: when you have these droplet density patterns with no overlap between the droplets, then you would anticipate, if you did a full many body calculation or some Gutzwiller or something, you will see that between these droplets, you will expect no phase coherence. Experimentally, when you calculate these kind of profiles and you can actually measure the phase coherence goes to 0. So it checks out that if you do not have overlaps without light and you make droplets that are distinct, clearly there is no global phase coherence. There is always intra-droplet coherence, that's clear, but there's no droplet to droplet coherence. But the point is when you introduce light, now it becomes interesting. I'm not sure. And the point is, if you had no dipole interactions with light, I can say for sure because of the laser, I will expect coherence, even if I have non-overlapping densities. Because it's like taking, if I have a K-wave board in my block function with an optical lattice, you would agree there is coherence there. I mean, you can see that. So you wouldn't say that there is no coherence there just because my density pattern dips. But now there is an interplay here, which unfortunately or fortunately can only be solved if I can do some kind of a many-body theory. And that is the next thing we should do. Ideally, next thing that Chinmay should do.
So maybe this is a bit of a vague question, but so in the BEC cavity systems, there was this deep connection with the decay model, right? And then that sort of really helped to understand these phase transitions and things like that. So in your setup, do you think there could be some mapping to this decay model kind of Hamiltonians and somewhat related is, what is the order of these transitions? Is there any?
So that's what we spent the longest time on. So we had these density patterns for the better part of last 7-8 months. So let me answer the two questions in serial order. First thing is about the Dickey transition. The reason why you can sort of map things to the Dickey transition in the cavity case is there is a very sharp single density wave mode you're exciting. So what you say is that that's a phonon mode. That's your optomechanical mode, or that's your oscillator, and you have light oscillator interaction, and you have a discrete model that falls out. So there's an easy mapping. So now with just the light wave Roton alone in this case, even there, it's a bit subtle. What is the sort of effective model you can write down? Because again, even though this K is sharp, the location of this K depends on the density itself. So it's not obvious to what is the single mode that I can write down and basically write down like a 2-mode Dickey type Hamiltonian. That is not clear. With Rotons, that's out of window. With the magnetic Rotons, out of window because I have a band of, so that's the problem. So then coming to the phase diagram and the thermodynamic order parameter, this is a bit hard because as I say, I don't know of a way to think of this in terms of phase transitions because as I said, both the standard thermodynamic limit or the sort of this infinite range interaction thermodynamic limit that I can take, both of them are completely uninteresting for me. In both these regimes, either my system's total interaction energy blows up or there is no competition. So this is a case where the thermodynamic limit in an interesting way is the most uninteresting part. So, but the point is still, these phases are like structural phases and there is very, I wouldn't say very sharp, Chinmay, you can correct me if I'm wrong, but there is a definite transition. We can write down some order parameters that change very nicely across these transitions. Maybe we could try and do some finite scaling analysis or something, but we just found that since the thermodynamic limit is not available, I didn't know whether I should go down. I don't want to talk about this as a phase transition. I had quotes on phases everywhere in my talk because of that. I don't think this is a phase transition in the conventional sense.